calculate mesons or others.
Hello.
Hi there.
Good morning, afternoon, evening. Do you see my slides? Do you hear me?
Yes, we hear you. We see your slides.
Okay.
Can you maybe put it on full screen? Or okay, it's more or less fine. But
is it fine like this?
Yeah, we can see it. Yeah, it's fine. Okay, so then we move on to Hervè Moutarde, who will talk about mechanical properties from GPTs. Please go ahead.
Yes. So, so basically, let me start with the home messages. I want to talk about the notion of proton internal pressure, and usually I will start by the home messages because basically we all have the three basic questions. Is it well defined? Is it a well-defined notion? Can it be really measured? And what are the needed theory inputs, either to perform this study, to get it from the experimental data, or to interpret it on a theoretical basis and learn something from QCD. And I will structure my talk in answer to convince you that it is indeed well defined, it can be measured. However, I will show you that there are a lot of problems here and there in the past between theory and data. I think that having further information on the GPD functional shape would be wonderful. Perhaps we will need only the X or T dependence on a given scale. Perhaps it would be enough. It's still an ongoing study, I would say. But in any case, even for the extraction, I expect the valuable inputs coming from either lattice or continuum QCD. And I'm not even mentioning all the required input for the interpretation of all this. So let me move to the theoretical framework. So basically, how do we do so? We start from the matrix element of the energy momentum tensor between hadron state. So here, for instance, I decided to write it in the bright frame, where I express this matrix element in terms of gravitational form factors A, B, C bar, and C, where the subscript A stands for either quark or glue contributions. Now, looking at this shape for an energy momentum tensor, I can put it in one-to-one correspondence with the expression of an anisotropic fluid, an energy momentum tensor of an anisotropic fluid in relativistic hydrodynamics, which means that if we were to consider hadron as a continuous medium, a relativistic continuous medium, we could establish such a formal correspondence. We have an energy density here, a tangential pressure here, and a radial pressure here. So basically here you see on this cartoon a definition of tangential pressure and radial pressure. And from this, we can define isotopic pressure as this weighted sum of tangential and radial pressure, and we can define the pressure anisotropy as the difference of these two quantities. Now, since, as I said, we have a one-to-one correspondence between these two expressions, it means that we can write a dictionary between the quantum picture and the relativistic fluid picture, and we can have expression for different parton types of all the quantities mentioned before. So energy density, radial pressure, tensor pressure, isotopic pressure, or pressure anisotropy. And all this depends on the gravitational form factors through basically Fourier transform. The explicit form of the dictionary, of course, will depend on the frame you are considering, but once you have set the rule of the game, if I may say, you can write this dictionary. Here, I will focus specifically on the last one of these relations, because as I will explain you, this is the one we can hope to get without any model assumption from experimental data. And so it will be the main focus of interest in the rest of the talk here. So how do we do it? We do it from the links between GPDs and these gravitational form factors. So I'll be brief on this, mainly to make it self-contained. We consider the Carl-Levin twist two GPDs H and E, and I write things here only for the sake of simplicity in the quark sector, but similar relation would hold in the gluon sector. And we observe that many moments of GPDs are related to the gravitational form factor CQ. And it was already mentioned in the talk before, we can get access to generalized parton distribution through deeply perturbed constant scattering, which means that in principle, we may get access to this gravitational form factor through electromagnetic scattering, which is good to know because it does not seem so trivial to have an experimental handle on the energy momentum tensor. So basically, just to summarize variables, I will consider a photon, a virtual photon with a large virtuality q square, which will scatter a quark carrying initial momentum fraction s plus psi. This quark will emit a photon gamma with momentum fraction x minus psi. Momentum transfer on the target is denoted by p. So at the end of the day, how we can read this? The Fourier conjugated parameter of the momentum transfer is the impact parameter in the transverse plane. So it tells us where the scattered parton is. This scattered parton carries fraction momentum x. And since we have momentum fraction x and psi live between -1 and +1. So all this holds in the Bjorken regime, which means that what is experimentally well defined is the so-called Compton form factor, which parameterizes the deeply vertical scattering cross sections. But when the virtuality of the photon q square is large and Bjorken x related to the skewness psi is fixed, then we can interpret this in terms of generalized parton distribution, and we have all the proof for this. So at the end of the day, the Compton form factor are integrals of the GPD on a coefficient function, which can be computed order by order in perturbation theory. So with respect to the energy momentum tensor studies and the extraction of pressure forces from DVCS data, the Compton form factors are the key tool, and we'll work with this in the first part of the talk. And in the second part of the talk, I will address more generally the question of how we can invert this relation to recover a GPD from a Compton form factor in a more general way beyond, the question of pressure forces. So, but first, about pressure forces, how does it work? We first start by expanding the so-called D term onto a basis of Gegenbauer polynomials, where we can read the evolution properties at leading order, at least depending on this factorization scale, quite easily. We can write dispersion relation for Compton form factors. This is a first principle relation, and it is a one subtracted dispersion relation, and we can express this subtraction constant by the difference between the real part of the Compton form factor h minus the integral of the imaginary part over this kernel, which is reminiscent of the Cauchy formulas in complex analysis. Then we compute the subtraction constant at leading order. So we plug basically this D term into the subtraction constant, and we observe that this subtraction constant is the sum over all these Dn coefficients here. And the first one of them, D1, is related to the gravitational form factor C, and we see at the bottom of our page that basically D1 for quark flavor Q is 5 times this gravitational form factor Q. So in principle, the whole approach is well defined from the theoretical point of view. We compute Compton form factors, we extract Compton form factors from the experimental data. From this extraction, we compute the subtraction constant. At the same time, we compute this subtraction constant in terms of the D term, and if we manage to extract D1, then we have a measurement of pressure distributions. So now let me start by how can we measure Compton form factors. So here it is a summary of the DVCS observables collected over the years and coming from all collaborations. You can see all of them: Hermes, Class, Rollet, Compass, Zeus, H1, and this is about as written beyond about 4,000 data point. in these 4,000 data points to be in the conditions of the application of factorization theorem, we took only a subset of them. So at the end of the day, we still worked with 2,600 measurements, and it's measurements about 30 observables. So a lot of various observables collected over a long time. So more precisely, if we look at the kinematic coverage of the observables, you see, depending on Bjorkenx here and Q square, basically all the fixed target experiments which are here and the collider experiments which are there. And so it means, and you realize this, that EIC and EICC are much needed, I would say most desperately needed, because there are only a few points here which do not represent much in the results of the fit, and the fit is controlled basically by all the experiment on fixed target. So if we want to get some more information on this part here, we really need to have these new colliders to constrain all this. And now if we further apply the kinematic restrictions to ensure we are in the domain of factorization theorem, so instead of looking at the existing data in terms of Q square, but if we look at in terms of T divided by Q square, you see here the enormous number of data points that we have to leave in order to make sure that increase our chances to be able to perform a leading t-test analysis of the existing data. But still, here we fortunately keep most of the collider data and collider kinematics. Now, in terms of results, we perform a neural network parameterization of Compton form factors, but describing independently real and imaginary part of Compton form factors. And then we propagate uncertainties all the way long, starting from replicas of experimental data and propagating these uncertainties all the way long until replicas of extracted imaginary part of Compton form factors. So here, for instance, in this plot, I show Xi as the imaginary part of the Compton form factor H depending on Xi over a wide range. So you see here that uncertainties explode, and it basically corresponds to, it's due to the fact that there's no data point here and there, but we wanted to be able to cover a broad range, and I will come back to this later on. You see that we managed to get a determination, rather clean determination of the imaginary part of H, but it's the well-known of all these quantities. The two dashed or dotted line correspond to phenomenological model, and this is one previous fit. So basically, I would say we're quite confident about the quality of the extraction for the imaginary part of H. We can do the same, of course, with the real part of H. So we can compute the DVCS dispersion relation. I insisted on the range of the kinematic domain probed by the neural network. Here, basically, we covered Xi between 10⁻⁶ and 1, T between 0 and 1 GeV squared, and Q squared between 1 and 100 GeV squared. We did so because if you look at the dispersion relation, we need to integrate over the whole range in Xi, which means that we want our neural network to provide us some answers in this range. And we had in mind to perform some impact studies for EIC or EICC and to consider data coming from existing colliders. So we needed to have a large level arm in Q square. So we can implement this integral, but instead of working between 0 and 1, we will integrate between 10⁻⁶, which is our lower bound here, and 1. And now we look at the subtraction constant here, and I will show you the subtraction constant either depending on T, and this is the leftmost plot, or Q square, and this is the plot in the middle, or Xi, and this is the plot in the right. I apologize for the mistake in the apparently stupid copy and paste mistake, but here, the kinematic, I consider this Q is 2 GeV squared, Xi is 0.2, and T is minus 0.3 GeV squared, which does not appear here because of this copy and paste. Basically, what you see that the subtraction constant does not depend on Xi as it should be from first principle. It should depend only on T and Q squared. And you see basically that it is reasonably constrained where we have data. So there are parts where the data and the error bounds are rather small, and where there is no data anymore. So for extreme values of Q square, for instance, or T, error bands get much bigger. And you already see one problems here in terms of the determination of the pressure forces. We have to perform a Fourier transform on the variable T. And if T is basically unconstrained, we can integrate over too large a range. So here, having some theoretical guidance on the T dependence, and this one of the messages I presented at the beginning, would be super useful. So let me explain you what our hypothesis here. We first do, as most people do, or I would say as everybody has done so far, that the subtraction constant is assumed equal to D1, which means that we brutally truncate the series to its first term. We will also assume, and it is frequently done in modeling, although there's no really good reason to do so, that this D1 coefficient is the same for all light quark flavors. We radiatively generate a gluon and charm contribution, which means that we'll start from a low scale, assume that there is no gluon nor charm, and radiatively generate them through evolution. And since we need an ansatz for the T dependence of D1, we will use a triple ansatz. The green curve here reflects the reduction of uncertainties in our fit result obtained by doing this triple fit and this triple ansatz. So you see here that there's one model dependent approximation, which is made, as far as I know, by most people involved in that game. And you see already a dramatic decrease of uncertainties by model assumption or say theoretical a priori. Nevertheless, doing so, we can obtain fits. And you see, I mean, subtraction constants was compatible to 0 within large error bars, and we get value of D1 compatible to 0 within large error bars, so which is expected. I would say unfortunate, but expected. And we can get also some expressions for some values for charm contribution, glue contribution. Here, this is a summary of our results. So depending on factorization scale on the abscissa, we show the sum of D1 over different flavors on the ordinate axis. The green band corresponds to our fit, and since we actually perform leading order evolution, we can see how things evolve depending on scale. And we put on this plot the different extractions that have been made so far, either extraction or model-dependent calculations. And you see basically that I think the aforementioned Giraud et al., Burkert et al. Point is this one, if I remember correctly. And this is the similar expression by Krasimir Kumeryski. So an overall agreement here. We provided in the paper, let me advertise it because we made it in order to be useful to the community. We provided a summary table of previous determination, either from Phenomenology, lattice QCD, or models, where we try to present the scale at which things were determined, uncertainties of the extraction, numbers of flavors, taking into account the extraction and the type of determination there is. And basically the markers here corresponds to the points there. And now let me just make some more quantitative comments on the uncertainties and systematic approximations that I made so far. Unfortunately, there's a lot of model dependence in the current extraction. First one, from my point of view, is that there's absolutely no justification for the truncation of the subtraction constant to the first term, which means that assuming that the subtraction constant is D1, and indeed, we tried to extract both D1 and D3 from the subtraction constant. So we still assume that D3 obey a triple ansatz in its T dependence, that it's the same for U, D, and S flavors, but we try to extract both D1 and D3 by separating them only through evolution. And you see this huge correlation. In fact, D3 is D3 plus D1 is approximately a constant. And you see here the 68% confidence level, and each point here corresponds to the different replicas we considered. And the green point in there is the results we get when we have only D1. So you see that in introducing the second term in the sum introduces a lot of uncertainties. In the same spirit, I mentioned before that we choose a triple ansatz for the t-dependence. This triple ansatz basically fixed through Fourier transform the shape of the pressure profile. And if you tweak the parameters of this triple ansatz, if you make it a multiple ansatz by changing the power here, you can see that the pressure anisotropy can vary by order of magnitude. So the actual value is extremely sensitive to the parameters we choose in this model-dependent approach. So in terms of theoretical issues, there's still a lot of work to do to improve things. There's many theoretical constraints of GPDs, but it's somewhat difficult to implement them at the compton form factor level. So we know that GPD reduces to PDF or elastic form factors. So there's a question of implementing positivity and polynomiality, which is still uncommon in modeling, although we know how to do it generally, starting from overlap of light front wave function. There's a need to use evolution equations to work, and indeed, from my point of view, I think that we should start working beyond linear order approximation, depart from the parton model to actually see what the impact of higher order QCD effects are, and it's we absolutely have to do it to prepare the ground for EIC and EICC. Another interesting study and would be the systematic impact of kinematic correction and DVCS, and to see how it changes the game. Now, as I mentioned at the beginning, I will generally address the question of the so-called deconvolution problem. So the question is, assume that we can extract the Compton factor H infinitely precisely from the data and on as many psi values as you want. The question is, how can we retrieve H, the GPD H? It turned out that this question was raised about 20 years ago, and from my point of view, it has remained essentially open, which means that when we looked at the literature, people thought that evolution would play a crucial role, but it was not clear whether in principle it was something which is feasible or not. It turns out that there exist non-zero GPDs, generalized pattern distribution, who have a vanishing forward limit and a vanishing Compton form factor up to alpha S square, which means that we can systematically build a generalized pattern distribution with a vanishing PDF or a vanishing Compton form factor at leading order, next to leading order. We speculate that it may be true at any finite order in perturbation theory, which means that if you think of the situation in terms of phenomenology, you start by defining a model at a low scale, you run an evolution equation up to a higher scale, and then systematically compare it to experiment. It means that it would be the residual powers, higher orders in alpha S that will prevent you from having this kind of non-vanishing term is the kernel of this operator. So at the end of the day, from my point of view, the deconvolution problem is ill-posed because you will always find that kind of non-zero GPDs hiding in the experimental data. And the same conclusion will hold most probably for several other hard exclusive processes, time-like content scattering, for instance, or meson production at leading order. And so yeah, I think from the theoretical point of view, we need to define and implement further criteria in the feeding strategy and to get some more information into what could be actually the functional shape of the GPDs to get rid of this uncertainty. So here, to give you a quantitative example, we call this GPD shadows GPD because they are there, but we do not see them. We see their shadow on the data. So we start with the shadow GPD at for the flavor U at 1 GeV squared, which means that by construction it has 0 CFF at leading order and next to leading order and 0 PDF at 1 GeV squared. Now we're evolving it up to 100 GeV squared using evolution in X space. We generate DS flavors and gluon contribution all the way along through evolution, and we compute the resulting Compton form factor. We would expect this Compton form factor to be a quadratic function of alpha strong because we killed the first term of the expansion, and this is indeed what we observed. So here we compute different values of the next to leading order Compton form factors. We separate it into its dependence on flavors and glue, and we perform a fit, and this is the blue curve is a quadratic fit. So you see that when alpha s is reasonably small, we indeed see that we have a quadratic dependence. And here you see the value on the ordinate, it's 10 to the minus 5, which means that if I take a popular GPD model used for phenomenology, for instance, the Kroll-Goloskokov model, and I plug different shadow GPDs and next to leading order. And if I look at a specific value, for instance, of psi is 0.1, and here is the X dependence of this GPD. So here there are two different GPDs on the plot. They are not very, they are close to each other. So you may say that it's no big deal and we should not worry. But you see that at psi is 0.5, for instance, the shapes are wildly different, with one GPD being large in the ELBA region and the other one being large in the DGLAP region are the same GPDs. And if I compute Compton form factors with these two GPDs, the difference of the Compton form factors at next to leading order will be less than 10 to the minus 5, which means that if perform a fit blindly from experimental data, we have no way to prevent these things to enter our numerics. So to conclude, in the quest towards proton mechanical property, concept is well defined and is suitable from phenomenological hypotheses. So I mean, it's good because I think there are not that many areas where there is such a clean path between theory, first principles, and experimental data. Here we can control systematically all systematic approximations. However, when we think generally about it, GPD deconvolution problem is ill-posed, which means that we will have to go, in order to avoid this problem, to multi-channel analysis beyond leading order. And I think that inputs or constraints from non-perturbative QCD would be beneficial, either working directly in terms of pressure forces or in the deconvolution problems. And I see the way through this by coordinated efforts using involving fits, different computing chains, and theoretical inputs coming from continuum QCD or lattice QCD. And it can go both ways. We can either try to use these inputs to constrain the fit, or directly compute things from first principles and then use computing chain to perform observables and confront our favorite models or theoretical predictions to experimental data and try to figure out what comes out from all this. Thank you for your attention.
Thank you very much for the great talk. So we have time for questions. Bowen was first. Please go ahead.
Thank you for the very interesting talk. I actually have a question about the hydrodynamics analogy that you made on page 3 of your slides. So my question is, in my opinion, hydrodynamics is kind of like an effective description of partonic degrees of freedom. For example, it has some assumption. For example, it assumes that the mean free path of those partonic degrees of freedom is much smaller than the size of the system. Can you justify this inside a proton for quarks and gluons? And another thing is that the price you pay if you choose to use hydrodynamics is that you lose the partonic interpretation. Do you aware of this price you pay, and do you have any comments on this? Thank you.
So yes, I agree with you. From me, I take it more, say, as a formal game to introduce, to define a notion of pressure in the proton than as a clear physical picture. So I will even say that when there are discussions about how the kind of pressure forces that we obtain here relate to confining forces, I don't know. So at least, and I think it is a cautious statement, that we can consider it as a formal way to define things like pressure. Of course, the picture is much clearer when we are in heavy ion collisions, where indeed we can anticipate that a fluid description will hold. Inside the nucleon in itself, we obtain orders of magnitudes which are sensible. I think that the picture has some kind of physical intuition. Now I share part of your skepticism about it, if that answers your comment.
Thank you. I just want to know your opinion. Thanks.
Okay, Victor was next.
Hervè, one question is, could you see any sound way to relate the scalar function ABC in the energy momentum tensor decomposition to the observable? And my second question is, right now we get a lot of statement about mass radius, charge radius, and mechanical radius of the proton. Is it correct understanding from your talk that considering uncertainty in this quantity, it is too premature to make statement about ordering between charge radius, mass radius, and mechanical radius?
Okay, so first question, we can extract C from an analysis in terms of Compton form factors, and in the spirit of what I have shown before, if we want to get A and B, we have to go down to GPD fits, which means that to get A and B, we have to solve the deconvolution problem, while if we are interested only in C, we can just live with this analysis I have detailed before. So it's doable, but there are still a lot of things to do carefully. And in terms of the ordering of these different radius, if you consider things in full generality, it's probably too soon to. Well, ideally, we'd like to say, when we said that we measure something, we'd like to say that this thing is independent of any parametric bias, and we would like to consider the extracted value as an interesting quantity, and then ordering would have a meaning. I don't think we are at this point now. I think that all the values which are provided carry a lot of dependence on theoretical bias, parametric forms, and so on. So either you have in mind when you look at the explicit values of how they are obtained and under which assumptions, and then you can start by looking at the comparisons, try to figure out what is brought by each of these assumptions, and try to see if these assumptions are sound or not. Or if you don't want to play that game, then I think it is safer to consider that all this is super model dependent at present.
All right. Are there further questions? I don't see any. No, there is one. Guy de Termont.
Yes, Hervé, thank you for this very nice talk. What would you need? I saw that you would need some input from, some help from effective light front wave functions. What would you expect from the community?
Yes, here because back to the point, if you look at the problems I mentioned here with these GPDs that can hide in experimental data, here basically what we used here was polynomiality, evolution, and computation of quantum factors. There's a key property of GPDs, which is positivity, that we haven't used so far. And if we want to put positivity in the game, then we would have to start with a formalism where both things are fulfilled at the same time. And the only way known so far to do it in a systematic manner starts from light front wave functions. So in the sense, yes, I think that that could be a valuable input.
Great. Thank you for.
Okay, thank you very much. So
Thank
let's
you.
close the session here. So thanks again, Hervè, and thanks to all the speakers.